So here is the final video on statics of rigid bodies in mechanics for A-level maths. So the question states a uniform rod AB of mass 6 kg and length 4 meters is smoothly hinged at A. A light inextensible string is attached to the rod at point C, where AC equals 3 meters, and to a point D vertically above A. If the string keeps the rod in equilibrium in a horizontal position and the angle between the string and the rod is 40 degrees, calculate the tension in the string, the magnitude and direction of the force exerted on the rod by the wall. So the first thing we ought to do, as we always do in mechanics, is to draw a clear diagram. So we're going to draw our rod going from here to here, and then at point C, so some arbitrary point here, all the way to here, we have the string at the point D. So let's draw in what we have. So we have some kind of, so just to make us clear that D is vertically above A, and then we've got the tension in the string like this, inclined to the horizontal at 40 degrees, and the weight acts in the middle, which is here. We're going to call that 6G, and we have 2 meters, and so from here to here, so we're going to call this 1 meter and 1 meter respectively. Here, make it more clearer. No, the diagram is not drawn to scale, but just for demonstration purposes. I've done that. Or actually, what I could do, I could shorten the line. That would make life a lot easier to make it realistic. So let's do that. So let's make it about the same here. So that's about 1 meter as well. That's more realistic now. So here we go. So we have that. So, and this is the point B. So what we ought to do is draw in our components in. So here we have our vertical component V, and we have our horizontal component H, like so. So we're going to mark those in as the vertical component V and the horizontal component H. Now really what happens when we resolve this force, we've got resolving horizontally is this, and resolving vertically we've got that. But if I leave it like that, the diagram will get a little bit cluttered. So this is how we really resolve the tension at 40 degrees, how we're resolving that force. But what we're going to do, for clarity, we're going to write the vertical component here, so it's clearer to read, and draw the horizontal like this, about there. So that way it'll be easy for us to read and the diagram won't get too congested. So that will be 2 sine 40 degrees, and that'll be t cos 40 degrees respectively. So now what we're going to do is take moments about A. So taking moments about A in a clockwise direction, we're going to say 6G times 2 is equal to 3 times 3 sine 40, and therefore T is 12G divided by 3 sine 40. We're going to get our calculator now and work this out. Write the true value out and then round. So let's get our calculator. So it's 12 times 9.8, 3 times sine 40. That gives me the following: 60.98. Four, 3, 7, 4, 0, 1, and that's 61.0 newtons, correct, to 3SF. Okay. So now what we're going to do, we're going to resolve vertically and horizontally. So resolving vertically, I'm going to get v plus t sine 40 equals to 6g. So v is 6g minus t sine 40. Therefore v is 6g minus 60.984 and so on sine 40. We're going to write the true value out here. So that's 6 times 9.8 minus 60.98, 437,401 times sine 40. And that gives me exactly 19.6. And then we're going to resolve horizontally. So if we resolve horizontally, we're going to get that h minus t cos 40 equals 0. It's in equilibrium. Therefore, h equals t cos 40. In other words, h is 60.984 and so on cos 40. Write the true value out, and then we're going to use Pythagoras. So it's going to be 60.984 437,401 times cos 40, and that gives me 46,716. So let's write the whole thing out. 46.71674,083. So we've got our horizontal component now. And what we're going to do is draw our components out. This is unneeded. So let's draw our components out. Let's see what's happening. So we have our horizontal component, which is 46.7, right? We have our vertical, like so. And we're now going to draw in the resultant force, like so, which is going to be in pink. That's our resultant. So let's write that in. So this is 46.716 and so on. This is 19.6, and this is theta, the direction of it, of the resultant force. So we can use Pythagoras. So let's do that here. That's 19.6 all squared plus 46.716 and so on all squared. Let's write the value out and then round. So we get shift 19.6 squared plus 46.716,740,83 squared, square rooted, and that's going to give me the following: 50.66175,948, and three significant figures. That's going to be 50.7 newtons. So we've got that rounded to three significant figures. And to find theta, we're just going to use tan theta, so the arctan of 19.46, sorry, 19.6, sorry, over 50 point, no, it's 46.716 and so on. So elongate that. And then we're going to get the true value on our calculator. So arctan, so 19.6, let's write the true value out, 46.716,740,83, and that gives me 22.76 and so on. Let's write the true value out. So that works out to be, therefore, theta is 22.8 degrees rounded to 1 decimal place. Well, in our case, we can say 3 significant figures as well, but normally we round angles to 1 decimal place. Here's a question for you to try. You can pause the video. When you're done, I will go through my work solution. Okay, welcome back. So the first thing we ought to do is draw a diagram. So this is almost identical to the example we just did. So we draw the rods, and at C, exactly in the middle, they tell us it's 2 meters, so I'm going to draw it roughly here. It's like that, and I'm going to try and make it more in the middle here. And we've been told that there's tension in the string, so let's draw it in. Climb to the horizontal at 40 degrees. This is A, this is D, just like before. Draw a dotted line here. We're going to have our components drawn in. That's our vertical component. That's our horizontal component here. Drawn in. We need to mark in the lengths, so it's 2 meters here up to this point. And from here to here is also 2 meters. It's not drawn to scale, but it's just a rough diagram. B. And then we need to have the weight drawn in. So let's do that. I'll just do the weight in green so it's clear. That's the weight. So we've got the weight here, 6G. And then our components here, T sine 40 is our vertical component. As I showed you the resolving before in the previous example. And the horizontal component, respectively, is T cos 40 degrees. Like so. So now, again, like before, we can take moments. So we're going to say part A. Taking moments about A, taking clockwise is positive. 6G times 2 is 2T sine 40. Therefore, T is 12G over 2 sine 40. Writing the full calculated display out is 91.47656,102, and they want the tension, so we're going to round that to 3SF, so it's 91.5. Therefore, T is 91.5, but we need to use the true value in subsequent calculations. That's been rounded correct to 3 significant figures. So now we're going to resolve horizontally and vertically. So resolving vertically, we can say that V plus T sine 40 is equal to 6G. So V is 6G minus T sine 40. So V is 6G minus 91.47 sine 40. Close that here. And that gives me nice V equals 0. So we do not have a vertical component. So horizontally, we're going to say the following. H minus T cos 40 equals 0. H equals T cos 40. So we get 91.476 and so on. Cos 40. Right, the true value out is 70.0751125. So the magnitude of the force is simply 0 squared plus 70.07 and so on, all squared. So we get 70.1 newtons, correct, 3 significant figures. So essentially what's happening here is we only have a horizontal component, meaning 70.1. There is no vertical component. So we can say the following. So we can say the force exerted on the rod by the wall is 70.1 newtons parallel to and towards the rod.